Here we have a picture of a cannon firing a cannonball in the horizontal direction. Okay, the cannonball starts out at 12 meters per second in the horizontal direction, and we're going to look at the position of the cannonball after delta t equals 1.6 seconds. We want to know how far the cannonball moves in the horizontal and in the vertical direction in 1.6 seconds. Now, as hopefully we're prepared to do from the previous examples, we consider a horizontal phantom object, horizontal phantom, moving at a constant 12 meters per second in the horizontal direction. Now, the reason this moves in the horizontal direction at a constant velocity is we assume that there's nothing in the horizontal direction to exert a force on the cannonball. Nothing around to exert a horizontal force on a cannonball to the right or to the left, so that the cannonball will continue moving without any change in its velocity. That isn't the case in the real world. There is air resistance, and we do have changes in x velocity, although in 1.6 seconds, maybe not that much change if you got a very dense cannonball. But I believe that in real world there would be a significant force, and it would have a significant effect on how far the cannonball travels. Okay, the other thing that we analyze is the vertical motion, imagining that there's a vertical projectile falling from rest, because the initial velocity of the cannonball is all in the x direction. It's all horizontal. There is no vertical motion, so that the cannonball is stationary with respect to vertical motion at the time it's fired. Okay, so that vertical phantom starts with an initial y velocity of 0 and accelerates at 9.8 meters per second squared. Okay? So we analyze the vertical motion of the cannonball. Okay, again, vertically, initial velocity is 0, so we have initial velocity 0. Acceleration is 9.8 meters per second squared, and again, we're analyzing this motion for 1.6 seconds. We conclude that the final y velocity then is obtained by this calculation and is 15.7 meters per second. The y displacement will be the product of the average y velocity times the time interval. If the final velocity is 15.7 meters per second and the initial is 0, averaging those two velocities will give us 7.85 meters per second, the average y velocity, which then multiplied by 1.6 seconds gives us the 12.6 meter vertical displacement. Now, implicitly, by saying that AY is 9.8 meters per second squared, we are assuming a y velocity in the, well, we are assuming, rather, that the positive y direction is downward, so that the 12.6 meter displacement will, as expected, be downward. Now, the x motion, and it looks like I've written y here where I meant x, so let's see if we can make that look a little more like an x. The x displacement is going to be characterized by the constant 12 meter per second velocity for 1.6 seconds and is therefore 19.2 meters. So that in 1.6 seconds the object falls 12.6 meters and moves in the horizontal direction at a distance of 19.2 meters. We could actually then calculate its direction at that instant. If this is the 1.6 second instant, the y velocity is 15.7 meters per second. The x velocity is still 12 meters per second. So we're going to have 15.7 meter per second y velocity, 12 meter per second x velocity, so that the velocity might be in a direction like this. Now, I haven't done a very good job of drawing these vectors to scale, but that's what we're going to see, that sort of thing. By looking at the y and x velocities, we can figure the resultant velocity and the angle with horizontal. Let's note that in general, if the initial y velocity is not 0, well, I'm sorry, this notes the final velocity. Okay. the magnitude of the final velocity is just the sum of the squares, the square root of the sum of the squares of the components of the velocity. That would be about 25 meters per second. The final angle is going to be the inverse tangent of the y velocity over the x velocity, and that calculation is also fairly straightforward.